Okay, so we're going to get started now with the chapter on stars. I'm not totally sure if we will get through all of this today or not. Probably not, but maybe. We'll see. Maybe we'll try and get through all of this and then do the activity first thing next time. But this covers mainly just the chapter on stars, but there's one section in the following chapter that's sort of covered. So to give you a picture of the stars that are near us, we actually already looked at this slide in one of the first two lectures, and this was our stellar neighborhood, anything that's near the sun within a certain range. And so some of these stars, as you're looking at them, and as I pointed out when we saw it the first time, appear to be sort of yellowish in color or reddish in color or maybe whitish in color or even bluish. And so those colors are actually real and how the stars actually appear. Moreover, some of them give off more light than others, right? So you've got little ones here like Gliese 876 that's not giving off a ton of light, but then you have very bright ones like Vega. Is that Aldebaran? I can't even read that. Here's Aldebaran, that are giving off a lot more light. And so the sun, in this scheme of things, even in our neighborhood close by, is not really all that spectacular of a star. It's just, not real big, not real tiny, and it's just a yellowish average star amongst this smattering here. Okay, and we talked about triangulation when we talked about Aristarchus and how he tried to estimate the size and distance to the moon and the sun. And you may be more familiar with this here on Earth whenever you see surveyors out that are trying to measure angles to things real precisely. And in doing so, they can figure out distances and where things need to be located. So triangulation is basically this idea of having some kind of baseline of a right triangle. This doesn't look like a right triangle, but this is supposed to indicate that it is 90 degrees. And so if you look at it on graph paper, it's easier to see that this is the same, this is a right triangle. This is supposed to be the same triangle. And so if you want to find this distance, you can use properties of trigonometry to help you based on this angle, figure out what this distance is. Okay, and like I said, the trig behind how to do that is not really important for you to master, just the concept that by figuring out what my baseline is, I know this distance and I know this angle, therefore using some properties of trigonometry, I can find how far away that tree is or how distant some object is. Okay, and this idea of triangulation, as Aristarchus did, has also been used to figure out the distance to the moon. And now that we are able to have global communications, we can get a wider baseline, which means our measurement's going to be a lot more accurate, and we can find the distance to the moon a lot more precisely using triangulation. If you've got one person on one side of the moon and one person on another side of the moon, and then you can work out the distance to the moon through triangulations that way. Okay, and like I said before, Aristarchus didn't have someone on the other side of the globe, so he's just trying to use this teeny tiny angle here to figure things out. And we talked about how he came up with an estimate of the distance to the sun and the distance to the moon, and the Earth-Moon distance he was a little bit closer to correct on than he was to the Earth-Sun distance, but nevertheless it was using this idea of triangulation even back in ancient times to try and get a handle on the distance to our nearest star, which is the sun. So that's one tool that we can do, we can use to find the distance to objects in outer space. But once you start talking about farther away objects like stars that are other than the sun, then it's going to be, you're going to be really hard pressed to get a wide enough baseline to find any kind of triangulation that you can work with and measure that angle. So another thing that is done instead is something called parallax. Parallax is again making use of a baseline, so to speak, but it's more of a visual effect rather than physically, changing your distance and trying to figure out angles. It's measuring, it actually is that, but it's measuring some effect compared to some background. Okay, so if you had a star nearby to you, then if you're comparing it to how the background stars look that are even farther away, then if you shift your baseline, then that close by star is going to appear to move. And the way that you can see this in your everyday life is if you take what I've drawn on the board there, maybe just pick out one of the moons in that lunar cycle and take your eyes and with one eye open, cover up whatever circle you're looking at. Keep your thumb at like arm's distance away and cover that up with your thumb with one eye open. And then if you switch eyes, you'll see, if you don't move your hand, that's no longer covering that object. Okay? And that's because there's a distance between your eyeballs, right? When I was looking at it from the perspective of my right eye, I was covering up that background thing. But then if I look at it from the perspective of my left eye, which is farther over, I'm no longer covering that thing up. Okay? And so we can use this idea of shifting and what we call parallax to see something about the distance. So let me show you a picture here of how it would work with stars. So let's say that we have a nearby star. By the way, there's not really a star this close to us. It's just presented this way so that you can see it. But to scale, it would be like, way off the screen, and we wouldn't even really be able to see that. But just so it's not to scale, but just to give you the idea, let's say that we had a nearby star that's close to our solar system. And then we're comparing it to really, really distant, far away stars, that are much farther away and don't appear to really move. So if we look at, in the direction of that nearby star at a certain time of year, say July, we look towards that star, and our eyes will line up then with some distant star over here when we're looking that direction. And then let's say we let 6 months go by and now it's January and we're at a completely different place in our orbit. So now our whole distance from the sun times 2 is this tremendously large baseline, so to speak, and we're in a different place in our orbit. If we look at that same star, it's no longer going to be, our vision isn't going to be directed this way. It's going to be lined up with a star over here. Okay? And so people knew that if the stars are sort of randomly distributed, we should have some nearby stars that appear to shift in relation to the background stars depending on when we look at them in the year. And even ancient peoples realized this and felt that, okay, well, if Aristarchus is right about things and, everything is really far away, then why don't we see some kind of parallax, some kind of shifting happening? They concluded that Aristarchus was actually wrong and that everything revolved around the Earth instead because they didn't see this parallax effect. But the reason that ancient people didn't see this parallax effect is that it's really, really small. Like I said, this isn't drawn to scale. We would have to put this way off the chart here. And so the angle, the amount of shifting that you see is really, really tiny. It's undetectable by your naked eye. And in those times, that's all they had was their naked eye. They didn't have telescopes. So you can't really see this shifting effect, this parallax, unless you have a telescope. So in those times, they concluded, well, Aristarchus must actually be wrong and everything must just be orbiting the Earth, when in fact he was right. It's just that we didn't have the technology then to know. However, with proper technology through a telescope, you can see this shifting occurring. Here's that same picture again. And now we're just like looking at it from on top rather than on the side. And here's the background stars. And we see that this star seems to line up with this set of stars during one time of the year. But during this time of the year, if we look towards that star, it lines up with this set of stars. And so this is what we would see through our telescope. In July, it might be near these 3 stars. but in January it's nowhere near these 3 stars, it's over here. Yes?
So it's not like necessarily that it's like a different placement of like one specific thing, but it's just like a different like set of like what's in the background of it?
Yeah, basically, it's like you can't tell from this picture that this one is necessarily closer, but knowing that it is, you see that it's shifting according to where the background, these ones in the background are farther away. And so it appeared to be near these 3, but then later in the year it's over here. And so you may ask yourself, well, then how do I know it's not just moving that direction? And so how you'd know that is then back when you came to July again, it would be back here again. You know what I'm saying? So it would go back to the relative position that I saw it here in July, and then in January it would repeat again. Okay? There are stars, in fact, we're going to see that stars actually do move too. So, you know, you do have to account for that possibility. But the fact that some kind of parallax is exhibited in a cycle like this is indicating that that star is near enough that, at least with our telescopes, we can see that shifting occur. Does that make sense? Okay. Okay, so I'm not going to make you work through all this. Don't be scared. I always like preface things with that, you know, because people tend to be scared of math. I don't know why. I don't think math is really that scary, but I guess it can be for some people. So, but anyway, this is kind of just showing how you can work out that distance a little bit more precisely. So, you know, once you have figured out, well, you know, when I was here in July and here in January, it appeared to shift this much, then I can work backwards and see what angle that makes, okay? And then that angle then is going to be related to this triangle. And then now I have a right angle that I can use, again, those properties of geometry and trigonometry to figure out the distance. Okay, and like I said, you don't need to worry about the details of this, but it's suffice to say it's solvable. You can figure out what the distance actually is. Okay, then, as we were just saying, these stars don't always stay in place themselves. They're moving also. So they may exhibit some motion across the sky that isn't cyclical or periodic, and instead indicates that they're actually moving. If they're moving towards or away from us, we call that radial velocity. And in that case, we're going to see some kind of Doppler shift occurring. But we may not see, it may not look like their position within a constellation has changed, because it would be as if, say, this bottom, in the top figure, this bottom right star was maybe like moving out of the screen towards us, right? Or into the screen away from us. But this dipper still looks the same. Okay, that would be if its motion is primarily radial velocity, moving towards or away from us. But if it's moving, say, across, sideways, then it's going to exhibit some amount of transverse velocity, and then that's going to change the shape of the constellation. So maybe this one here is, what does it look like? It looks like this one here might be moving that way, okay? And then over time, if you look at the second image, it looks more like this because it moved that way in a transverse way, okay? Most stars will not be completely transverse motion or radial motion. There'll probably be some combination of the two, right? It's slightly moving towards us, but over to the right or something. And so over time, the shape of these constellations will not stay the same. Of course, it takes a long time for them to change, at least in terms of a human lifetime. But the constellations, as they look today, will not always remain that way. This is, I think, one of the dippers, and so it's going to change and maybe ultimately look something like this one day. Okay, so here we go with another clicker question. See if you can reason your way through this. We didn't really explicitly say it, but think about baselines. That's the hint I'll give you. Feel free to draw something if that helps you. Anyone else want to change anything? All right. So we got different answers. Okay, so now I've got to see what the right one was. I need to remember to look at that before I bring this up. Okay. So most of you said it looks like, most of you said A. That's interesting. So let's see if we can reason our way through this. So if the distance to the sun is smaller, what does that do to our baseline? Does it make our baseline larger or smaller? Small. It's going to make it smaller. So, you know, if this, you could think of it as like chopsticks or something. If they're spread this far apart, this is your baseline. You got a bigger angle here. If they come closer together, it's a smaller angle. So the correct answer actually should have been B.
So the parallax angle is the opposite. Okay. The reason why I picked it is because I was thinking that the parallax angle was the base angle, the 90 degrees. I thought it was the one that was on this side. So like not this up here.
Oh, I see what you're saying. Okay. All right, I'll consider going back and maybe giving you credit if that's what you were thinking. Is that what you were thinking too?
So, like, can you draw it? Like,
Sure.
Yeah, just to show.
Because I'm a little confused.
So here's the sun, and here's maybe two different points during the year. Okay, and you're looking at this star here, and it's going to appear to shift like this, and so, you know, this is the angle that we're talking about. Technically, the parallax angle is half of that. Okay, so this is what we call as the parallax angle. But as this whole angle changes, then the half angle will change as well. So let's make it now where they're much farther apart. And here's that same star. Okay, and now we can see that the parallax angle is bigger, all right? You see it now? Okay, so yeah, if you were thinking that it was like this angle, I guess that might be different, but yeah, it's just like half of this whole thing. And so as you get farther apart with your baseline, that angle's going to be larger and easier to measure. So that has implications for other solar systems. For example, imagine a cooler star with a planet that, in order for intelligent creatures to live on it, that planet would have to be closer, orbiting closer to its star if the star is cooler. Does that make sense? And so its baseline is going to be smaller. So it would be more difficult for civilizations to notice a parallax angle if you were orbiting a cooler star than, or like if you lived, if you could somehow live on Mercury and you're closer to the sun, you're not going to see the parallax as much. Whereas if you were to somehow be able to live on Jupiter, you'd be able to really notice the parallax because you'd be farther away and your baseline would be larger. Okay, so I don't know. I think it's interesting because I always wonder, well, you know, if there are other intelligent civilizations on other planets, what are they able to notice in their night sky? And are they able to see the same things as us? And I don't know, parallax could depend on how close or far away they orbit their star in order to get a baseline that could be noticeable. Okay, I'll go back though and I'll give you credit if you said A, because if that was confusing.
If you just go back through your slides, did you explicitly state the angle was though? Is there a couple
Yeah, right here is where it's stated. Yeah,
Yeah, it's fine.
yeah, but that's okay. I may not have highlighted that quite well enough, so we'll go back and yeah, and then here, I guess. This is a specific example of a parallax angle that's 1 arc second. But in any case, I'll go back and accept that as an answer as well. Okay, so then getting back to, we've talked a little when we were talking about light bulbs on our tangent there about luminosity and how much light something is giving off. But the luminosity that something gives off may not tell you how bright it appears to you. If you have someone shining a flashlight in your face and they're like 2 feet away from you, that's going to seem really bright, even if there's someone that has a tremendous spotlight and they're like, a mile away. That's not going to seem as bright to you as that tiny little flashlight right in your face. And that has to do with the fact that how we register brightness doesn't have to do with how much light doesn't only have to do with how much light is given off, but also how far away is that light, right? So the closer something is, the more bright it's going to appear, even if it's less luminous than something farther away. And you see that in this picture right here. Alpha and Beta Centauri are stars that give off a tremendous amount of light, okay? Comet Halley here is just a little piece of rock, right? It doesn't even give off its own radiation really, other than glowing by virtue of burning up from being near the sun. But it's not producing thermonuclear reactions and giving off energy that way. It's not producing anywhere near the luminosity as Alpha or Beta Centauri, but you see it looks almost as bright as them. And that's because why? Well, Alpha and Beta Centauri are 4 or so light years away, whereas Comet Halley is within our own solar system. So luminosity and brightness are kind of distinct in that sense. Luminosity is just how much light does it give off. I don't care about how far away it is. How much light does it give off? Brightness has to do with how much light can I actually see. And that's going to depend upon the luminosity, but also upon the distance that the object is from me. And light drops off really rapidly with distance. I think we talked before about how that relationship goes as the distance squared, inversely. So if I have an object located at a certain distance away from something that's emitting light, and then I move it 3 times farther away, rather than being 3 times dimmer, it's 3 squared, it's only 1/9 as bright as what it was before. 9 times dimmer, in other words. Okay? So here's a graph of how that would look, right? If this is your initial intensity, it would drop off really rapidly as you move your distance, right? This is distance on the x-axis, and this is your brightness or your intensity. Okay, and so the brightness then, like I said, is inversely related to the distance squared, and here's the luminosity here in the numerator. So it has to do with both the luminosity and your distance, and that 4 pi in there is just a constant, so you don't need to worry so much about that, but your distance is the thing and the luminosity that are really important for how bright something is going to be. And so astronomers have devised different systems to quantify how bright something appears. And so there's something called the magnitude system, which tries to quantify this idea of brightness just the same way that we were quantifying luminosity with watts or lumens or whatever. The magnitude has to do with how bright it appears to me. And so they do it on a sort of backward scale where the lower the number, the brighter the thing is. So here in the Little Dipper, here to the bottom right, you see a star that's 2. It's got a magnitude of 2, which means it's actually very bright compared to this bottom left star that is 5, See how much dimmer that is. So the larger the number, the dimmer the star in terms of a magnitude scale. Okay, then just to confuse things a little bit more, there's something called absolute magnitude. Now, absolute magnitude is not actually the same as brightness. Now we're back to the idea of luminosity again. Okay, so apparent magnitude is how bright it apparently is. Absolute magnitude has more to do with a certain luminosity. And what this luminosity is if I leveled the playing field and put every star at a certain distance away from me, namely in this scale system, it turns out to be 10 parsecs away. If I put every star that distance away, how bright would it appear to me? So you're still bringing in this concept of brightness, but really it's getting a handle more on luminosity, because at that point everybody's the same distance. So if something is more luminous, it will be brighter to you. We would never have the situation where it's more luminous and it appears dimmer, because it's the same distance from you as something that's less luminous. So in absolute magnitudes, you're really getting a handle on luminosity without actually saying the number of watts. You're just saying, well, if I put that star 10 parsecs away, how bright would it appear to me? But I'm putting every star 10 parsecs away, so, anything that's more luminous will be brighter, if that makes sense. Okay, so did we discuss this? I feel like we brought this up already. Oh, question.
Yeah, just on the last one. So basically, this is just like taking out the factor of distance.
Exactly. Yeah, it's kind of like the celestial sphere in that respect, that you're just imagining some specific distance that everything is located at. Okay. I believe we talked about this already. Did we talk about this? Yeah, I thought we did. Okay, so Wien's law and Stefan Boltzmann's law, I think we discussed in our intro about light. And so this idea I want to bring up again because it has to do with stars, that when you have something that's bluer, that has to do with a more luminous star and also a hotter star. So here's the brightness or luminosity, and here's the temperature. So bluer is hotter and more luminous. Okay, so that's kind of, I'm combining these two laws into one. The bluer being hotter I'm connecting the two. So bluer being more luminous is the Wien's law, and then that luminosity will tell you about the temperature, which is Stefan Boltzmann law. Okay, but depending on the color of the star, you're going to have this characteristic black body curve that peaks at a different wavelength corresponding to a different temperature and a different brightness. Okay, and so here's a smattering of different kinds of stars, and I'm arranging them here by color, where I've got blue stars on the left and red stars on the right, and colors in between are in between. And so the hotter, bluer stars are here, the cooler, redder stars are here, but notice some other differences. This blue hot star is much larger than this tiny little red star that's cooler. And so why are they this way? Why does it turn out that if I arrange them by color, they're also arranged by size and temperature and all of those things? So we're going to try and connect the dots first to their size. Okay, so let's see if we can reason through this. If you've got a more massive star, if you've got a bigger star, it's got to be more massive, right? And so you can think of it this way. If it's more massive, it's got more fuel that it can burn. And if it's got more fuel that it can burn, it's going to burn it hotter and more intensely, because that mass is going to heat up the core even hotter, right? Because remember when we were talking about the sun and that inward pull of gravity being responsible for the core being so much hotter? Well, the more mass you've got there, the hotter you can get that core temperature, and then you're going to burn through everything hotter and more intensely. This is like a very fuel inefficient vehicle, right? Think of this as your Land Rover. okay, and here is your smart car or something, okay. On the red end of the spectrum, then, you're not going to have as much mass to burn, and you're cooler, and so you're going to burn that more slowly. Okay, you're not going to burn through as much fuel as quickly or as intensely. Okay, so one thing also to note, I have these letters here that seem maybe cryptic, and we're going to talk about what those mean. They indicate something about the spectrum of each of these stars. It turns out that this color and this hotness and this intensity also has to do with the spectrum we would see from that star. And there was an astronomer named Annie Jump Cannon who, early part of the 20th century realized that we can actually classify these stars according to their spectrum. And she said about doing this, it was almost like, she said about doing it like a biologist might set about classifying different species of animals. She didn't necessarily make any assumptions going in about how one might be related to another or other factors that they might be related to. She literally just looked at the spectra and said, okay, all of these ones have really strong hydrogen lines. I can also see some calcium and magnesium and iron, but hydrogen is the strongest. So I'm going to put them all in the same category, and I'm going to call that category A. And then I see these other stars, they all their spectra exhibit these prominent lines, which are kind of different from these ones. So I'm going to call this category B. And she kind of went through alphabetically that way to start with. And then it turned out that some of the categories were actually maybe, just actually a subcategory of something else. So some of them merged, and so that's why you don't see A, B, C, D, E, F, G. And then later on, it became understood that the spectral categories also told you about the temperatures. And so since she sort of started in a somewhat arbitrary way and just called this, okay, this is category A, then later on it was realized that, well, actually, if I arrange these according to temperature and color, then A really isn't the first, but O is the first. Okay? So then later on, rather than rename all of her categories, they just rearranged them and kept the categories the way they were. Okay? So O stars turn out to be the hottest and the bluest stars, and also the largest stars that you'll see. Okay, so O is our hot blue large category. M is our tiny red category, and that's what we were seeing here below. People have come up with ways to remember this. Astronomers say O, be a fine girl or guy, take your pick, kiss me. I think that's a terrible way to remember it, but O, be a fine girl, O, be a fine guy, kiss me. Whatever. When you were memorizing, if anyone did, like, in music class, memorize Every Good Boy Does Fine, or did you do that to memorize the lines on the staff? Okay, so it's a similar idea. It's sort of arbitrary, but if you want to come up with your own saying, I challenge you to come up with something better, because I think that one's pretty terrible, but whatever helps you remember it. In order from hottest to coolest, or bluest to reddest, that's the way it goes. And so where is our sun in the scheme of things? We are a G star. If you remember nothing else about this scheme, I always tell people, remember that the hottest is O, the coolest is M, and us is G. OMG. You can remember that, right? Okay? Hottest, coolest, us. OMG. But, also you can remember the sayings if that helps you as well. Okay, so another clicker question. Starting to run out of time. Hopefully we can get through this. Just try to keep straight in your mind the difference between apparent and absolute. That's my hint. All right, are we all in? This time I'm going to look at the correct answer before I click stop. Okay. Looks like most of you said A, which is the correct answer. The apparent magnitude is different from the absolute magnitude. The absolute magnitude gives you a little bit of a sense of the star's luminosity, although it doesn't measure it in watts. But the apparent magnitude has to do with just how bright is it apparently to me. That's the way you can associate it in your mind. Okay, so apparent magnitude has to do with brightness. All right, let me see how far we have to go, because we may need to save some of this for next time. We'll go a little bit farther. I still don't know if we'll get through all of this, but we'll see. So this diagram here looks a little bit crazy or confusing, and I'm going to take a little time to carefully explain what it is you see before you. This is known as Hertzsprung-Russell diagram. Sometimes people just refer to it as an HR diagram, H for Hertzsprung, R for Russell, HR diagram. And what it does is it tries to organize the stars a little bit more clearly. So we saw when we lined them up from an O star to an M star that there were changes in color and changes in size. And then I kind of wrote below that, yeah, also they're hotter or cooler or more or less luminous. But this diagram tries to keep all of that information in one place. So on the, on the bottom here, we have those spectral classes that we were talking about before, O, B, A, F, G, K, M. And on the y-axis, we've got the luminosity of the star. Is that in watts? Oh no, it's in solar units, so compared to the sun. Okay? And if you take a random sample of stars, say stars in our solar neighborhood, and you plotted them according to, okay, their x coordinate will be, based on their spectral class, their y coordinate will be based on their luminosity, and then I'm going to pluck them right onto this coordinate system, then I'm going to see a pattern arising where most of the stars that I have plotted on here fall along this curved line. You see that? Now there are some exceptions. You've got a few up here in the upper right-hand region, and you've got a few in the lower left-hand region, but most of them, the vast majority, fall along this almost diagonally curved line here that we call the main sequence. This diagonally curved line called the main sequence basically represents where stars live for most of their lives. Okay? For most of the sun's life, in other words, it's going to be a G star with, one solar luminosity, and that's the end of the story. Okay? Later on, as we're going to see, it's going to become much, much bigger and brighter, and it's going to become a giant star, and it will no longer be on this main sequence where most of the stars are. But these stars are near the ends of their lives, and they don't spend very much time on there. That's why we see fewer of them there. Okay? And then these stars on the bottom left are like stellar corpses. So they're already like deceased stars. So again, we don't see as many of those. Most of the stars we see are kind of in the primes of their lives. You can think of this as stellar adulthood or something. Okay? That's where you're going to be for most of your life. And it's hard to see on this particular slide, but do you see how there are lines going through diagonally? You see those? Those represent the radius of the star. So anything along this line here is the same radius as the sun. Anything along this line here, I think, is 10 times the radius of the sun. Anything along this line here is 100 times. Anything along this line here is 1,000 times. Anything along here is about 1/10 of the sun's radius. So, you know, these red stars are only about 1/10 of the size of the sun. And then these ones are like 100th and 1,000th and so on. Okay, so there's a lot of information contained on an HR diagram. And so, again, main sequence represents where most stars spend most of their lives. This giant phase is the geriatric stars that are aging and about to die. And then these white dwarf stars are stellar corpses that are like deceased stars, as we'll see why they're considered deceased later on. And where you are along the main sequence, let's say you're like most stars and you're along the main sequence, depending on where along this main sequence, you're going to live a longer or shorter lifespan. For example, up here, Spica is along one of these radii measures that's like 10 times the size of the sun, or not quite, and it's at least 10 masses of the sun. And so its lifespan, this larger star, is going to burn out in a shorter amount of time than, say, the sun. See how the sun says 10 to the 10 years? This one's only 10 to the 7 years. So these are trying to draw them, you know, in terms of these ones are littler than these ones, and the bigger ones are going to die faster than the little ones. Okay, because they're burning through their fuel faster, basically. Here's another Hertzsprung-Russell diagram for you without all of the labels and lines, so maybe this one's a little bit easier to look at. It also doesn't change the size of the stars along the way, but we kind of know in the back of our minds that these ones are bigger than these ones. And again, you see that most of the stars lie along this main sequence. You've got some older aging stars here in the giant or supergiant realm, and then you've got a few white dwarfs here that are deceased stars. Oftentimes these little red ones are called red dwarfs. Okay, they're not like white dwarfs in the fact that white dwarfs are deceased. Red dwarfs are in the prime of their lives. They're just all small, and so we just call them all dwarfs. Okay, so here is another clicker question. Try to picture that first Hertzsprung-Russell diagram. I wonder if I can actually go back to that without, will this still? Maybe that'll help you think about the question a little bit. Look at the relative sizes and then reread this question. All right, are we all in? Okay. So it looks like everybody put C, which is correct. Hopefully my toggling back there helped you. The caveat being that when we're talking about these size relationships as depicted here, we're assuming that our stars are lying on the main sequence, because if we go back to the Hertzsprung-Russell diagram, here we see that in the supergiant realm, some of these M stars are actually huge, right? But that's because they're in the dying stages of their lives. They're not on the main sequence. Some of them might be bigger than a blue star. but you know, that's an exception to the rule of the stars that live most of their lives on the main sequence. So that's the caveat that we needed. Okay, I think maybe this is a good place to stop for today, and what we'll do is we'll return to this next time. I'm just giving you a little bit of a warning. Try to keep this fresh in your mind, because I think the next slide is another clicker question. So we'll have to make sure you're aware of everything that was said before that. You want to do one more?
Yeah.
Let me just see if that's the last one. Oh yeah, okay, why don't we just do that? Does anybody have an objection? Too late. It's already up there. Let's start responding. And try to keep in mind the difference between luminosity and brightness, by the way. Anyone else want to change? Are we good? Okay, I'll wait. All right, we good? This one's a little trickier. Let's see if we can figure it out. Looks like most people put D, and D is the correct answer. Okay, so if you were just thinking it was brightness, you might have been thrown off here and said, oh, well, it's closer. That's why, you know, it's so bright. But in actuality, we're talking about luminosity, so, you know, distance really doesn't enter into our thinking. It has to do with the size of the star. And again, if we go back here, we see, for example, that Betelgeuse is only 3,000 Kelvin. It's in this M class of stars that are cool, but look how high up it is on the y-axis, which is luminosity. And why is it so luminous? Well, because it's really large. So there's a lot of surface area to radiate and give off light. Okay, so that was the correct answer to that clicker question. So again, I think this is a good place to stop now that we got both the clicker questions in. I don't know, there might be a few more on this PowerPoint for next time, but I think we're out of time for today, so we'll just say leave well enough alone. I will see you again on Wednesday.